So section 4.1 is going to discuss the minimums and maximums of a function. And so there's a little bit of vocabulary that we're going to have to learn here at the beginning. Stuff that maybe you've seen before, maybe you haven't. But one of the things I want to try and emphasize to begin with is definition of a local min or a local max. Those two are on your handout. Local min basically is a place on the graph where the value of your function is smaller than anything near it. So on the example that I've given you, we've got a couple local minimums here. This is a local minimum on this graph right here because it's smaller than any value near it. Now, is it the smallest value that the graph gets to? No. The smallest value that it gets to is what's called the absolute min. So this is an absolute min because the function doesn't get below this. This is just a relative min or a local min. I use those two interchangeably. A lot of times I'll probably use relative min, but they mean the same thing. Likewise, over here, you've got a local max. So this is a local max because it's bigger than anything near it. Now, is it bigger than anything overall? No. Looks like the function keeps on going up and up and up, in which case this is just a local max. It's not an absolute max. I tend to call them global mins and global maxes for the same reason that I call them relative mins and relative maxes over here. But, you know, it's just a different term for the same thing. Now, let's look at these and try and establish what these are. What could we say about the point here at B? What kind of a point is that amongst all the different points that I've outlined? Local min, local max, absolute min, absolute max. Yeah, it's a local max. And how about over at C? What's going on at C?
Local min.
Local min.
Yep, that's a local min. And let's assume that this graph ends right here and right here. The graph doesn't continue in any way. What could you say about this point here at D?
Absolute max.
Yeah, thank you. It's an absolute max. And then these endpoints over here, this endpoint here, be an absolute min. And if you want to be picky about it, this is a local max. It's bigger than anything near it. Kind of in part by default, right? Because you're cutting the graph off there, but it is a local max. Okay. All these points, the local mins, local max, global min, global max, have something in common. Other than the endpoints, these interior points are either at a place where the derivative is 0, or what's going to happen with the derivative of the function at C?
Is it undefined?
Yeah, thanks, Matt. It's undefined. So at C, the derivative doesn't exist. That's because you've got a corner point there. Other reasons that the derivative might not exist would be that you have a vertical tangent, or that the function is undefined at that point, or it has a jump at that point, a discontinuity of some sort. So the interesting points that we want to look at in the function can kind of be classified as critical points. And critical points are going to be numbers for your function such that the derivative is 0 or does not exist. And that's going to be the first task that we're going to set ourselves to, is finding such critical points for different functions. Okay, and I think I sent you out a little PDF of some of these problems that we're going to look at. So is this it? Yeah, this is some of them. Where's the rest of them? Not seeing them. Sorry about that. Well, I guess we're gonna have to do it kind of old school. Nah, no, we'll do it this way. Find the critical numbers for, let's see, f of x equals x cubed plus 6x squared minus 15x. Now, the nice thing about our first example here is that it's a polynomial. It's defined everywhere. So we don't have to worry about any endpoints or places in the domain where the function is not defined. Actually, places where the function is not defined, values of x that aren't in the domain. So the search for critical numbers really turns down to figuring out where the derivative of this function is 0. That is, where does f prime of x equal 0? So what's the derivative of f of x?
3x squared plus 12x minus 15.
Excellent. And if we're setting that equal to 0 and solving, personally what I would do is I try and do a little thinking rather than pull out the quadratic formula. I mean, you could use a quadratic formula. It's like burning down a house to roast a pig, but you know, it'd work. For myself, I'll factor out the 3, which is going to be a lot easier because now I can see how this thing factors. X and an X, a plus and a minus. What two numbers multiply to -5 and add to 4? That would be 5 and 1, 5 and -1. Now we're not quite done. You've got this times this times this equals 0. 3 can't equal 0, so we'll ignore that. What are my two solutions for x?
-5 and 1.
Yeah, thank you. -5 and 1. And those are my critical points. That's where interesting things should be happening with respect to the function. So if we go out to say Desmos, let me just open up a new Desmos screen and graph this, we should see either minimums or maximums at those points. Dirty little secret, you don't even need to type in y equals. It just assumes that y equals is there. So x cubed plus 6x squared minus 15. And let's try and get this picture in view a little bit better. Oh, 15x. Whew, there we go. I was looking at that going, wait a minute, that doesn't match my expectations. All right, but there's two interesting points that we can see on the graph here. One of them is right here when x equals -5. See, you got a point up here that's a relative maximum. And then when x equals 1, you've got a relative minimum. So beautiful. Relative min and relative max. Didn't even have to have Desmos to figure that out. We could figure that out just by looking at the derivative, that we knew that those points would be there. Let's continue and do another one. Example B. Let's take a look at f of x equals cosine of x for x between -3 pi over 2 and 3 pi over 2. So I want to find the critical values for that one. First thing I'm going to need is the derivative. So AC, what's the derivative here? What's the derivative of cosine?
Negative sine x.
Negative sine x. Excellent. Now notice that there's a negative there. AC nailed it. If it starts with a C, it gets a negative in its derivative. That means your trigonometric functions of cosine, cosecant, and cotangent, when you differentiate them, are all going to have a negative sign. I want to know where the sine is equal to 0. I want to know that in the interval negative 3 pi over 2 to 3 pi over 2. I'm not sure how you want to do this. How well do you remember your trig? You could remember that sine is the y coordinate of your point on the unit circle. So you could think of it geometrically. So the y coordinate is going to be 0 at points like this, here and here. That's where your y coordinate is going to be 0. Does it matter that I have this negative out in front? Really, it's negative 1 times sine of x. But negative 1 can't be 0. So the only thing that can be 0 is the sine function. If you're looking at the unit circle and trying to ask yourself, well, where could that be 0? It could be 0 when sine is 0, so when your x is 0, or x is pi, or 2 pi, or 3 pi, etc. You just have to assure yourself that you're in this range. So let's list all the different values of x where the sine is 0 that are in here. So let's think about that. That'd be 0, pi, 2 pi is too far. So 0 and pi in one direction. If I go the other direction, I get negative pi. Negative 2 pi, again, is too far. So it's just these 3 points that are going to be where the sine is 0 in the interval negative 3 pi over 2 to 3 pi over 2. I hesitate to show you this. In a face-to-face class, you're not going to be able to do this on an exam, but you can do these things in other ways. Let me just show you with a graphing calculator. Let me clear this out. Our calculator is in radian mode. Calculus is done in radians. You should have that all set up. Let's plug in the cosine function, cosine of x. And I'm going to graph that between, say, negative 3 pi over 2 and 3 pi over 2. I'm also going to graph, well, actually, I don't need to graph 0. Let's set up our table, our window. I want to go from negative 3 pi divided by 2. Now, when I hit the enter key, it's just going to give me a decimal approximation. It's not going to give me any nice symbol using pi anymore. That's okay. And 3 over 2 is 1.5. So I'm just going to type in 1.5 times pi. So negative 3 pi over 2 to 3 pi over 2. X scale tells you where you're going to get tick marks along the x-axis. Now, right now, I've got to set up for units of pi over 2. That's not a bad place to leave it. Let me just show you that that's indeed what I've got. Pi divided by 2 is going to give me 1.57. On the y-axis, I know that cosine goes from negative 1 to 1. So that should be some good settings. When you get those settings, hit the graph key. Make sure that you're in radian mode. And in this interval, let's see, right? 1, 2, 3. In this interval, I can see 3 places where it's got a min or a max, right? And those 3 places would be right here, and right here. We can also add to this graph the graph of our derivative, negative sine of x. And we should see a nice correlation between our conclusions and the graph of the sine function. The sine function is 0 at 3 places, right here, and here. And those correspond to where the function has minimums and maximums, respectively. You can trace the trace key and type in a value like, say, pi, second pi, and there's your minimum there. Or if you click the up arrow, then you see that, oh, okay, yeah, the derivative is 0 here, that corresponds to a minimum here, and so on. We could type in negative pi. Still tracing. You see where the derivative is 0, again, corresponds to the function in blue having a minimum point. Okay. So a couple easy examples, warm-up examples to begin with. Are we okay with those first two? Something about them that maybe I went over too quickly? Does it help to have a graphing calculator to look at here a little bit?
Yeah.
Yeah.
All right, that's good. I'll keep on doing that a little bit. Make sure that you got a nice visual for this as well. Let's move on to another critical point. If this were right out of the book instead of out of WebAssign, then it would be problem number 40, I think. Yes. So, but for us, we'll call it example C. And that is G of theta equals 4 theta minus tangent of theta. And again, you want to find the critical values here. So, okay, let's see what we can do. Now, one thing you got to be clear about is that critical values can't happen where the function doesn't exist. And with the tangent function, 4 theta minus, I'll just give you a quick reminder, 4 theta minus sine of theta over cosine of theta, you're going to have problems in the tangent function where the cosine is 0. And the cosine of theta is going to be 0 when theta is a multiple, an odd multiple of pi over 2. So the domain is all values of theta such that theta is not an odd multiple of pi over 2. Now I'm writing this out just to be kind of user friendly so that when you look back at your notes, it'll make sense what that is. Mathematically, you could let k be any integer. So numbers like -3, -2, -1, 0, 1, 2, etc. Then odd integer or odd multiples of pi over 2 would look like this. Theta such that theta is not equal to 2k minus 1 times pi over 2. This is just a fancy way to write odd numbers. You can't have a critical point someplace where the function is not defined, and it's just not defined at odd multiples of pi over 2. So 3 pi over 2, 5 pi over 2, 7 pi over 2, those kind of things. Those are odd multiples of pi over 2. All right, let's get back to solving this. We need to differentiate this. To find the critical points, g prime of theta. Maybe somebody can help me out here. We're going to differentiate with respect to theta. So unlike our last section, we're not going to worry about an implicit differentiation. We're differentiating with respect to this variable. That's not a 40, it's a 4 theta. What's the derivative of 4 theta with respect to theta?
4.
4. Thank you. Does anyone remember what the derivative of the tangent is?
Secant squared.
Yeah, well done. Secant squared. All right, so I want to know where this is equal to 0. Okay, that's kind of a pain, but we'll have to work with it. Probably what I would do is I would take the secant squared and move it to the right-hand side first. Can anyone suggest a reason why I'm moving that to the right-hand side?
Get rid of the negative.
Yeah, it becomes positive over here. Secant squared of theta. So we get rid of the negative there. And then I'm going to take the square root on both sides to solve for secant of theta. That's going to give me 2 equals secant of theta. But if you're paying close attention, you realize I've made a mistake. There's 2 solutions, plus or minus there. Most of us probably wouldn't be happy working with the secant. So let's remind ourselves that the secant is the reciprocal of which function?
Cosine.
Cosine. So turns out I want to know where cosine, 1 over cosine is plus or minus 1 over 2. I'm going to do something that I usually don't do. I'm going to take the reciprocal on both sides. I mean, technically what you're going to do is multiply both sides by cosine and then divide by 2. But we'll end up being the same thing. We'll end up with cosine of theta is going to be plus or minus 1/2. Those are going to be all, or it's going to be where this has a solution is going to be your solutions to where this function has a critical point. Now, I'm sure everyone has handy their favorite unit circle. Let's remind ourselves, cosine was which coordinate on the unit circle? You're looking for cosine of theta. Which one are we looking at? The
X.
x coordinate. The x coordinate. Thank you. So I want the x coordinate to be 1/2. That happens at 300 degrees and at 60 degrees, but this is calculus. So I wouldn't choose 300 or 60 as my answer. What would I choose instead?
Over 3 or 5 pi over 3.
Yeah, you got to choose your answer in radians. Pi over 3 and 5 pi over 3. Those are both places where the x coordinate is 1/2. Where's the x coordinate negative 1/2?
2 pi over 3 and 4 pi over 3.
Yep, right here at 2 pi over 3 and again at 4 pi over 3. So my solution here is pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. No, 4 pi over 3. Yes, last one is 5 pi over 3. That's just in the unit circle. But I could go around one more time and get another solution. Or I can go around again and get another solution. So I guess if you're trying to be very, very accurate, then what you would have to include is plus multiples of 2 pi. So plus n, or I guess the last time I used k times 2 pi plus 2 pi times k, and so on. Because there's an infinite number of places where that's going to occur. let's take a look at the graph real quick and see if that matches, see if it matches our expectations. Mhm. Kind of a funky looking graph. Here it is. But let's see what kind of points we've got here for minimum points. There's your 2 pi over 3. There's your 5 pi over 3. There's negative pi over 3. Let's see, there's a couple maximums as well. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3, and so on. You can see that there's no end of these kind of solutions. Each of these has a minimum and a maximum. And they're all at multiples of pi over 3. So they continue on forever. Since they didn't limit the domain in this problem, they didn't say just look between 0 and 2 pi. That's why we need to add on that multiple of 2 pi stuff. Is because there's an infinite number of solutions there. Nice. Comments on example C here? Anything that's a little bewildering? Maybe I went over a little too fast. I guess I'm treating this as if we're in a face-to-face class. This is really example D. G of x is the cube root of 4 minus x squared. Now, can you have a negative number underneath a cube root?
No.
Yeah. Actually, under a cube root, you can. For instance, the cube root of -8 would be -2, because -2 cubed would be -8. So you can do that. Whereas if I was dealing with a square root, say the square root of -16, well, you can't say that's 4 or -4. You have to go into complex numbers, which we're not going to do in this course. Now, the first thing you want to look at is the domain for these functions. Well, I just said that we can put in negative numbers here. You can take the cube root of a negative number, so there's really no restriction. When you're looking at the domain, you want to look for things that you have to avoid. So you want to avoid 0 in the denominator, 0 in the denominator. You want to avoid negative numbers underneath the square root, or negative numbers under an even root. So square roots, 4th roots, 6th roots, etc. You want to avoid negative numbers underneath there. And you want to avoid the log of a number less than or equal to 0. You can't take the log of 0 nor anything less than or equal to 0. Those are the big pitfalls you got to avoid when you're working with the domain. But none of those apply here. There's no place that you're going to have a 0 in the denominator. This is an odd root, so you don't have to worry about that. There's no logarithms here, so the domain is everything. In fact, if you looked at this graph, you'd see that. So let's take a look at this graph. And it's right here. So cube root of 4 minus x squared. And you can zoom out and see that this graph is defined forever. It goes on and on and on, et cetera. But of course, the interesting part is near the origin, closer to the origin. And those are the critical numbers. Let's see if we can't find those. To find the critical numbers, the first thing I need to do is take the derivative. And before I do that, I'm going to rewrite this. How am I going to rewrite the cube root of 4 minus x squared?
Can you write it?
Or
to the
minus x
1/3?
squared to the 1/3.
You're going to raise this to the 1/3 power. So a couple voices there. I appreciate that. The derivative, this is where your chain rule comes in. You've got to do the derivative of the outside. The outside function is this cube root. So it's going to be 1/3 times 4 minus x squared. 1/3 minus 1 is going to be -2/3. But that's not it. What else do I have to multiply by in differentiating this?
Inside function.
Derivative of the inside function. Thanks, Jed. So derivative of the inside function. Somebody tell me the derivative of the inside function.
-2x.
-2x. Thank you. Now I can clean this up. The -2 stays in the numerator. This and the 3 are in the denominator. So it's -2x over 3 times 4 minus x squared raised to the positive 2/3 power. Like that. My goal is to find the critical points, and this is what I need. The critical points are where one of two things happens with the derivative. Either the derivative is 0 or the derivative is undefined. So the derivative equals 0, g prime of x equals 0 when the numerator equals 0, when -2x equals 0. Well, when is that? Oh, come on. When does -2x equal 0? What value of x?
0.
0, thank you. Or g prime of x does not exist when the denominator equals 0. So that would be 3 times 4 minus x squared raised to the 2/3 power equals 0. So a little bit more work here. I'll start by dividing both sides by 3 and get 4 minus x squared to the 2/3 power equals 0. And really, this is only going to equal 0 when what's inside here equals 0. So basically, this turns out to 4 minus x squared equals 0. You could also think of raising both sides to the 3/2 power. That would cancel out that. And then 0 to 3/2 power would still be 0. What could x equal?
2 or -2.
Yeah, thank you so much. 2 or -2. There's plus or minus 2 there. So the critical points are going to be x equals 0, x equal 2, and x equal -2. Those are our critical points. That's where interesting things in this function are going to happen. Now, you're not guaranteed to get a min or a max at those points, but it is still going to be a place where something interesting is going to happen. So let's take a look back at the function and see what's happening there that makes it interesting there. So let me zoom in. Can someone explain why I'm getting those critical points? What's interesting that's happening at these functions that relates to the critical points that we got? I'll start. At x equals 0, you've got a maximum, and you've got a horizontal tangent line. So that's why we got x equals 0 as a critical point. But why do we get 2 and -2 as critical points?
Vertical tangents.
Yeah, vertical tangents, exactly. The function has a vertical tangent here and here at 2 and -2. So it's undefined, even though the function is nice and continuous at that point, it has a vertical tangent. It's undefined at that point. All right. Let's keep going. Something happened to my handouts here a little bit. So earlier I talked to you a little bit about Fermat, and what brought Fermat into mind was that the book calls this Fermat's theorem. I'm not familiar with it being a Fermat's theorem, but they call it Fermat's theorem. I'll take their word. Too bad their spokesperson doesn't know how to pronounce his name. What we're going to do with this last part of our work here is try and find the minimum or maximum of a function. Now, we're going to assume that we're working on what's called a closed interval. That is, we're just going to look at a function from 2 to 6 or from negative pi to pi over 2, something like that. That's a closed interval, so brackets at the endpoints. We're also going to assume that the function is continuous, and that's a big part of this. It doesn't work if it's not a continuous function. If it is a continuous function, then the minimum or maximum occurs at either one of 2 points. You're going to have to look for 2 sets of points and evaluate the function at those points. The first one is the critical numbers, or the critical values. And the second one is the endpoints of the interval. And a lot of times people forget one or the other. And I'll tell you this very blankly, or very bluntly, that is, when I set up my problems, I usually set things up so that one of the critical points, that is one of the minimums or maximums, is going to occur at a critical point, and the other one occurs at the end point. Because I want to see, do you remember to test it at both points? You have to look at both sets of points to find either your absolute min or your absolute max of a function on an interval. So with that, let's look back at a problem that we already did a little bit of, which is this one. So now I'll call this one example. What are we on now? Yeah, lost track. Are we on F? Maybe. Example, don't know. All right. F of x equals x cubed minus 6x squared plus, actually, you know what? This isn't one that we've done earlier. It's close to one we did earlier. Plus 5. Find the absolute min and max on the interval -3 to 5. Okay. Here's what I want to see on an exam. Here's what's going to get you credit anyways. You might get the right answer just by, a brute force approach, but this is what I'd want to see. This is what's going to get you credit when you hand in your notes. First of all, since this is a nice polynomial function, the domain is everything. It's all reals. It's -infinity to infinity. So we don't have to worry about that. If there was some holes in a domain, you can't have a critical point where a point's not in the domain, but we're okay there. F prime of x is 3x squared minus 12x. And I'm going to start by finding my critical points by setting that equal to 0. Suggestions as to how you solve this. Personally, I'd factor out a 3x. You've got something times something equals 0. One of those somethings have to be 0. At what values of f do I have a critical point?
0 and 4.
0 and 4. Thank you, Jed. 0 and 4. Now, to find the absolute min and absolute max of the function, I need to test 2 types of points. this is the first one. So I'll call these points A, and this is the second one, B. I need to test the function at both of these points. So here's what I'm going to do. I'm going to list these points. We'll do -3, 0, 4, and 5. And then I want to plug in f of x. So I need to plug these into my function, and I'll wait here while you take out pencil and paper and do that. All right, fine. Let's use some technology here. On the graphing calculator, let's clear this out. And I'll clear this out as well. Start by typing in y equals your new function. Let me clear out these other functions. So my function was x cubed minus 6x squared plus 5, 6x squared plus 5. And just a reminder, if you're going to do this on the graphing calculator like this, that you want your windows, you want your table set up the proper way, you can check that with second and then window. Make sure that independent is set to ask, dependent is set to auto. The other settings don't matter. When that's set, hit the second key, then the table key. If there's stuff here, you can delete it. Just hit the delete key. And now let's type in our numbers. -3, 0, 4, and 5. And let's write down these numbers. -76, 5, -27, and -20. So this would be a perfect one for an exam. They wanted you to find the absolute min and absolute max. There's your absolute min right there. Where's your absolute max? What's the biggest that this function gets on this interval?
That's
Right
0.
here.
5.
Yeah, it gets up to 5 at x equals 0. That's your absolute max. And that's it. Notice that these numbers came from different types of points. This was an endpoint. This was an interior point. So, okay, that's great. My point is you have to test both sets of points in order to find the absolute min and absolute max. You can't always count on a graph. A graph is nice. If you think you'd find a graph helpful, I can do a graph for you right here. But there's your absolute min and there's your absolute max. Actually, you know what? It'd be pretty convenient just to do this graphically on your graphing calculator. What I would do, since you've already got the rest of this set up, is just adjust the window. The window is going to go from -3 to 5. It doesn't have to go any farther because we don't need to see it any farther. And then the rest of it, hit zoom and then 0, and there's your graph. And you can kind of see what we saw looking at the table. It starts out pretty low, it gets up to its maximum, and then you get a relative minimum, and then the endpoint. So it follows along pretty closely. The strange stuff here on the y-axis is because I didn't take time to choose y scale very carefully. Y scale is where we're going to have tick marks, and the graphing calculator is trying to crab in about 81 or 82 tick marks on that axis. If I make it something bigger, like let's go 20, then the graph won't look as messy and crowded. Just keep in mind that each one of these tick marks is units of 20. So -20, -40, -60, and so on. Nice.
How do you know what numbers to put in for X?
You mean in terms of what I had here?
Yeah, those.
Great question. And that's getting to the heart of the matter. there's two sets of points. This first set was your critical points. And I have those here and here. And the other one were the endpoints. So you need both. You need to investigate what's happening at the function at both of those sets of points, the endpoints and the critical points.
Okay, thank you.
Yeah, so any minimum or maximum has to occur at one of those points. It cannot occur at anything else. So that's good because there's an infinite amount of points. And if we had to test an infinite amount of points, it would probably run out of time. So.
Well, we need to be providing you with like the actual work of plugging in every X value, or could we just use our calculator for that?
Great question. I expect and encourage you to use your calculator. Yeah, I mean, there's a lot of grunt work that I just don't want to see or need to see. I think I can trust that you can plug those into your calculator. But this is pretty much what I would expect to see on your exam a week from today, is something like this. I mean, that's how I would have to solve it. And I think you should be solving that in a similar way. If you got some shortcut or something like that, something different, yeah, I don't know. You should be telling me ahead of time rather than surprising me on the test and then telling me afterwards, oh, I learned this in Khan Academy. Well, no, this is pretty straightforward. In fact, we'll do another example like this.
I have a question. Sorry to
Yeah,
interrupt.
please, go ahead, Kate.
When you're taking the derivative for that one, why did you drop the 5 at the end?
Oh, does someone want to answer that? What's the derivative of 5?
0.
0.
0. Yeah, derivative of constant 0. So
Okay, because I had it written down on another one that we kept when we did example A.
oh my.
We kept the 15 and then took out the 3.
Because
that's what I thought, but then we did that, so I got kind of confused.
We had a 15x. So derivative of x is 1, so that's why this term just.
Okay.
So it's a good question. Yeah, good question. And if we can put that one into mystery solved.
Thank you.
Yep. Okay. Let's see. Give me a second here because I want to do at least one more. Okay, so one last example. And example, dunno, number 2. Let's see. F of x is going to be x over x squared minus x plus 1. And we're going to look at that on the interval 0 to 3. Want to find the maximum of that function on that interval. Now, one of the things I do, especially in a face-to-face class, sometimes to help you out, is I'll give you like the derivative ahead of time. It's like, okay, look, I know you can use the quotient rule to find the derivative. That's fine. Here it is to help you out. And what this does is it means you don't make a mistake in calculating the derivative, and it tests you, do you understand the rest of this? So the rest of this would be figuring out, all right, well, where is the derivative equal to 0 or where is it undefined? And then following through with this part and testing the endpoints and the critical points. So our job right now is to find the critical points. Well, the critical points on this one are going to be where the numerator equals 0 or the denominator equals 0. Where the numerator equals 0, the derivative is just going to be 0. You have a horizontal tangent. Where the denominator equals 0, now the derivative is not going to be defined at that point. Let's start by figuring out where the numerator is equal to 0. So that is 1 minus x squared equals 0. Or 1 equals x squared. What does x equal?
-1 and 1.
Good, plus or minus 1. In the interest of time, let me tell you that x squared minus x plus 1 equals 0 has no real solutions. Real solutions. That means that f prime is always going to be defined. There's not a value of x for which f prime does not exist. So that brings us to the point of testing. These are our critical points, and these are our endpoints. We got to be a little bit careful in setting up our table. Does anyone see why? We're trying to maximize the function on 0, 1. In what way do I have to be careful about setting up our table?
It starts at 0, so but
Exactly.
there's also -1.
Yeah, so when we're trying to find minimums and maximums, we're not going to look at -1. It's just not a part of what we have to focus on. So all we have to do is test these 3 points. Now that's the endpoints and the critical points. But the only critical point we got to test is the one that's actually in the interior of this function, or in the interior of this interval. The rest of it is just setting it up and doing it on our calculator to try and find what's the absolute min, what's the absolute max. So I'll just do that here. Actually, I got to do it in here. Again, I'm going to hit the alpha and then the y equals key. That way I got a nice numerator, denominator. And I'm going to type in, ooh, good question. What should I be typing in? Should I be typing in the function or its derivative?
Function.
The function. Excellent. Because we're trying to put these points in the function. It's an easy mistake to make to type in the derivative. Because we do so much work with those, you kind of get in a little bit of a groove. So x over x squared minus x plus 1. When you're ready, you hit the second key and then the table key. And let's see, let's plug in values of 0, 1, and 3. So there you go, 0, 1, and 3/7. That's all the information that we needed there.
So why don't we include -1?
Great question. -1 isn't in the interval. We're trying to find the maximum of this function on this interval, so we don't have to look at -1.
Yep.
All right, cool. Now, I don't know if you noticed it or not, but on that decimals link I gave you for this problem, what I did is I said, you know what, let's restrict this function to just looking at the values of x that I need to, from 0 to 3. So I didn't need to look at -1. I could. There'd probably be something interesting happening there. Let's take kind of a quick peek. There you go. So at -1, looks like the function has a minimum. That's okay. I don't want to look there. I'm going to keep my restrictions and just look at it on the interval. So you see you got a minimum here, a maximum here, and kind of a local min here. All right, so as far as the answer is concerned, this is your absolute min, and this is your absolute max. Now I realize you can get the right answer just by looking at the graphs of these things, and that's fine. I'm not going to penalize you for double checking your work, but I still need to see some calculus, okay? I'll make a deal with you. I'll keep the problems reasonable. You show me the calculus. I mean, if you're not wanting to show me the calculus, I'll make these problems really hard that you have to show me the calculus. but that's not the way I roll. I always have this agreement with my students that I'll keep them easy. You just show me the work. All right.
How many questions should we expect on this exam?
Ooh, I guess it depends if I have a good weekend or not. Yeah.
Okay.
Yeah. I don't know. I try and keep it reasonable, you know. I'd say anywhere from like 15 to 25-ish, you know. I'll try and get out an exam review for you as well. But yeah, I haven't started on any of those yet. Okay, anything else here? All right, that'll do it for this section.